Welcome to this lecture in EE557. In the last lecture, we have seen some examples about Markovianity or Markovianness. In this lecture, we are going to see the first assumption that we are going to usually make in order to preserve the Markovian property of a stochastic system. So let us start with the definition of the stochastic system. So I have xk plus 1 is equal to fk, xk, uk, and the process noise. And yk is equal to hk, xk, and I have the measurement noise here. And we know that the input in general can be selected as a function of all of the previous and the current outputs. So in the last lecture we have solved two examples. In one of them the process noise was independent. It was a white sequence and it was independent with the initial condition x0. And in the second example, we had seen a system in which the process noise samples were correlated in time. And in the second example, we have seen that the Markovian property could not be preserved. So in that case, we lost Markovianity. And in the first example, we had Markovianity. And in these two examples actually showed us that the independence of the process noise sequence would play an important role in preserving Markovian property of a stochastic system. So that is going to be the first assumption that we are going to make in order to preserve the Markovian property. Let us say that this is an assumption. And I will call this assumption as assumption A. So this is an assumption for the basic random variables of a stochastic system to preserve or to have the Markovian property in that system. So the basic random variables x0, w0, w1 going until infinity, and I will also assume the independence of the measurement noise sequence. So I have v0, v1 going until v infinity are all independent, So this is going to be called the assumption A, and this is going to be one of the assumptions that we are going to use to preserve Markovian property in a stochastic system. Let us see immediately what this type of assumption would bring us. So lemma. This lemma is going to tell us that the transition PDF, one-step transition PDF, would have a Markovian property when we have this assumption. If assumption A holds, then P of xk plus 1 given x0k and u0k is equal to P of xk plus 1 given xk uk. So you see that in the given condition on the left, I include all of the previous state sequence and all of the previous input sequence. And on the right, I have, in the given conditions, I have only xk and uk. So when the current state and the current input are given, I could actually remove the previous states and the previous inputs from the given condition. So this holds if assumption A holds. So now let us look at a proof of this property. So you see that this is only a one-step transition PDF of the system. So for the system to have a Markovian property, we need to have all different steps of transition PDFs would have this property. Okay, we have m-step transition PDFs having this property for a system, for a stochastic system, to be Markov. So this is only part of the Markovianness in this case. So let us look at the proof. In the proof, I'm going to look at this distribution. I know this distribution is going to be the distribution of xk plus 1. This is probability distribution of xk plus 1, given x0k and u0k. And here, as the argument, I will give an arbitrary subset of the state space here. And we know that by definition, this is nothing but the probability of xk plus 1 inside capital Xk plus 1. Given I have those given conditions, x0k and u0k here. Okay? If I can show that distribution corresponding to this PDF is the same as the distribution corresponding to this PDF, then because I can always convert a distribution to a density, assuming that the density exists, then I would have my result. So here, in order to be able to show this, I'm actually going to continue substituting xk plus 1 from that formula here. So I have, this is probability of, instead of xk plus 1, I write fk, xk, uk, and wk here. Okay? This should be inside xk plus 1 subset given x0k and u0k here. So here, the xk and uk are already given to us. Okay? xk and uk are already given in the conditioning. Okay? So these parts of this function are already determined by the given conditions. Here, therefore, only wk is stochastic here. All right? So I can actually write this event, this function of some variables being inside this subset, this event only in terms of wk. So here, let me try to illustrate what I mean here. Let us say that, remember the earlier example that we have solved, where we had the first example that we solved, where we had the independence assumption or the process noise. In that case, this function was this, xk plus uk plus, and I have wk. Okay? And in that case, we have calculated the CDF, which required the probability of this event, xk plus 1, smaller than or equal to psi k plus 1. Okay? But I can actually write this event as follows. xk plus 1 is inside the subset minus infinity and psi k plus 1. Okay? So this is in the example that we solved, this is my xk plus 1. Okay? Small xk plus 1 should be inside this interval. This is a subset of my state space. And if I compare those two expressions for this specific example, this is my capital Xk plus 1. But we know that instead of xk plus 1, I can write this in that example. xk plus uk plus wk is inside, let me write here. I will write smaller than or equal to psi k plus 1. This is the same thing of being inside this interval. And remember, because this xk and uk is given in the given conditioning, I could take this xk and uk to the right-hand side as deterministic variables. And I have written this as this condition, psi k plus 1 minus xk minus uk. Okay? But what is this? This is an event for the random vector, the random variable wk, and here this event can be written as wk being in the subset minus infinity psi k plus 1 minus xk minus uk. Okay? So you see that I could write this event in terms of xk plus 1, which was the event of xk plus 1 being inside this subset. I could write it in terms of wk being in another subset here. Okay, I will call this as wk being inside capital WK, and you see that this new subset is going to be dependent on xk and uk. Okay, so then this event is equivalent to this original event here, because xk and uk are given to us. Similar to this, I can make the same manipulation here. So function of wk being inside capital xk plus 1 can always be written in terms of an equivalent event. And this equivalent event, it can be written as wk being inside the subset capital WK, which depends on xk and uk, okay, given x0k and u0k here. And how do I define this WK here? I define this WK set as follows. So I will just here write the definition of WK. WK is the set of W's such that this condition is satisfied. Fk, xk, uk, wk inside capital xk plus 1. This is the definition of my subset capital WK. Here, this subset, this WK, is nothing but the set of W's for which this condition is actually satisfied. For which this condition is actually satisfied. Okay? So then I can actually continue arguing here. So what are these x0k and u0k? I know that x0k as a whole is really nothing but a function of which random variables. So I can actually write that x0k is a function of x0. So I will write here a function. I don't know what type of letter I should use here. Let us use the letter S here. x0k is really a function of x0, w0, w1. So going until which w here? I know that the largest index of x here is xk. Okay? And I know that xk can only be a function of wk minus 1. Okay? So all of the states here, they are some function of these random variables. Of course, here I can say that x0 is only a function of this one, x1 is only a function of these two, x2 is only a function of these three, etc. Okay? But xk is going to be a function of these random variables. What about u0 case? u0 case, in that case, so let us say this is the function s1, it is a function of s2, of which random variables? I can say that it is going to be a function of x0 in general. Why? Because u0 is a function of y0, and y0 is a function of x0 and v0. Okay? So here you see that u0 is going to be a function of x0, v0. And what about u1? u1 is going to be in general a function of y0 and y1. And you see that y0 is already a function of these. And what about y1? y1 is a function of x1 and v1. x1 is a function of x0, and it is also a function of w0. All right? And u1 can also be a function of v1. all right? Because it's a function of y1. So you see that these are going to continue like this until which basic variables? uk is going to be a function of yk, or from y0 to yk, and in it I will have wk minus 1, and I will also have just vk. Okay? So these random variables are going to continue until wk minus 1, and they are going to continue, v's are going to continue until vk. So we see here that these random variables, these x0k and u0k, they are functions of these basic random variables. But so we here assuming the independence of these basic random variables. And here I see that this wk is independent with all of these earlier variables. Okay? So wk, which this event is based on, is independent of all of these basic random variables. Okay? So wk is going to be independent of these x0k and u0k as well. All right? That means that this event, these given conditions, do not give us any information here except for the values of xk and uk here. So I can actually remove these given conditions from this probability due to the independence. So I'm going to continue with the equality here. This is going to be p wk inside capital WK, xk and uk. So I keep xk and uk dependence here, and I remove all of the conditions. But what is this? This is going to be the probability distribution of wk evaluated at the subset capital WK, xk, uk. Okay? So we see that here we have written this distribution in terms of the probability distribution of the process noise wk, which is evaluated at a subset which is a function of xk and uk. Okay? So we see that this final result is only dependent on xk and uk, and it doesn't depend on the other given conditions here, which are x0 to k minus 1 and u from 0 to k minus 1. Let us write this. So I will write which only depends on xk and uk in the given conditions. Xk and uk. That means that this probability distribution that I started with is only a function of xk and uk, and it is not going to be a function of x0 to k minus 1 and u from 0 to k minus 1. That means that this distribution here, or this probability, is nothing but xk plus 1 being inside capital xk plus 1 given xk and uk. That is going to give me the same result here. Okay? So that means that p xk plus 1 given x0k, u0k, evaluated at capital xk plus 1 is equal to p xk plus 1 given only xk and uk evaluated at the same subset. But what does this mean? This means that these distributions should be equal. These PDFs should be equal as well. because I can always extract PDFs corresponding to these distributions. So this is quite good. So the independence assumption would bring us some information. So it would bring us some property which would make the one-step transition PDFs to have, which would enable one-step PDFs, transition PDFs, to have Markov property. But what about the M-step transition PDFs? If I make only this assumption, will the M-step transition PDFs, will they have this type of property? Unfortunately, the answer to this question is no. So this assumption is not going to be sufficient for making M-step transition PDFs have Markov property. Okay? But there are going to be some special cases. One of the special cases is the case when all of the inputs are deterministic. Okay? If there is no feedback and U0, U1, going until infinity are all deterministic. In this case, this property, the assumption A, can be shown to actually result in the M-step transition PDFs to have this type of property. Okay? I'm not going to show it here. The proof is going to follow very, very similar line of reasoning. And if there is no feedback and if all of the inputs are deterministic, then this lemma can be generalized to M-step transition PDF. And the lemma can be generalized to M-step transition PDFs. Okay? So I can write xk plus m given x0k to u0k. So I will write here k plus m minus 1. Okay, I need to give all of the states until time k, and I need to give all of the inputs until time k plus m minus 1. This is going to be equal to p of xk plus m given only xk and u from k to k plus m minus 1. Okay? And this is going to be true for all m larger than 0. If all of the inputs are deterministic, then we can say that M-step transition PDFs would also have Markov property. But on the other hand, this would tell us that actually if there is feedback, then we might have problems. So that is actually correct. If when we have feedback, then M-step transition PDFs might not have this type of property, even if assumption A is satisfied. Okay? Even if assumption A holds. And in order to be able to explain to you the problem that we encounter in that case, I will here solve another example. So let me say that let the system remain here because we might use it. This example is also this example is also in the book, so you can check it. example is as follows. x1 is given w0. So here we are given this equation. We know that the state at time 1 is a function of xk, at time 1 is a function of x0, u0, and w0. Here this function is just given as w0. And x2 is w1. And x3 is x2 plus u2. These are the three state variables. So now you can actually understand what is the function f0 here. f0, x0, u0, w0 is w0. And f1, x1, u1, w1 is just w1. And f2, x2, u2, w2 is given as this function, x2 plus u2. So the question example still has some more statements. Suppose that the output is equal to the state, and suppose that the first two inputs are selected deterministically to be equal to 0, but the input at time 2 is selected as a function of y0 and y2. Okay? We know that the input can be a function of current and the previous outputs. So we here say that the input at time 2 is summation of the current output plus the output at time 0. We can always apply such feedback rule. But y0 is equal to x0 and y2 is equal to x2. So I have here x0 plus x2. Okay? Here we are going to make the assumption A. Assume that here you see that there is no measurement noise, so the assumption A would amount to the process noise and the initial conditions are all being all independent. So I have x0, w0, w1 going until w infinity are all independent. Okay? Here the task is as follows. We need to find two PDFs. The first PDF that I need to find is x3 given x01, u02. And the other PDF that I would find is x1, u12. Okay? So you see here that when I compare these PDFs with these ones, I'm selecting m is equal to 2. This is a two-step transition probability because here I have x1 and I have here x3. Okay? That means that my k is equal to 1 in this case, and m is equal to 2. All right? K plus m is 2, k plus m is 3, so I have x3 here. If these two are equal, then we are going to say that two-step transition probability would have a Markov property. All right? The first thing that I'm going to do is to remove these inputs here. These inputs, u0 and u1, they are both equal to 0. And you see that none of the variables here are dependent on u0 and u1. Okay? So here, u0, u1 conditioning is really unnecessary. So instead of this first PDF, I will calculate the following. x3 given x0, x1, this is this information, and I will discard u0 and u1 because none of the variables here would be dependent on u0 or u1 and they are both 0. As a result, I would have here only the input u2 remaining. Okay? And from here I can remove u1. It is unnecessary in the condition. It doesn't give us any information and none of the variables is dependent on it. So I have x1 and u2 here. Okay? So now let us try to find these two distributions, these two PDFs. By the way, this example and the coming reasoning is going to be quite difficult. So it might be necessary to review both the notes and this lecture several times before you can understand the main meaning or the main aim here. So now let us first try to concentrate on the first PDF here. In order to be able to calculate both, I would need an expression for x3. x3 is going to be, it is x2 plus u2. I know that x2 is w1. And u2 is given as x0 plus x2 plus x0 plus x2. You see that x2 is again w1. So I have 2w1 plus x0. This is x3 given in terms of the basic random variables. So now let us concentrate on the first PDF. In order to be able to calculate this PDF, I will first calculate the corresponding CDF. This CDF is going to be this one. CDF of x3 given x01 and u2 and u02 this is going to be, okay? And I will write this here, the argument psi 3. This is going to be the probability of x3 being smaller than or equal to psi 3, CDF definition, given x0, x1, and u2. Okay? Let us substitute x3 into this expression here. P of 2w1 plus x0 being smaller than or equal to psi 3. This is the event that I need to calculate the probability of. Given x0 is given, so one of the components of this sum is given here, and x1 is given. x1 doesn't appear here, and u2 is given. Okay? So now let me try to look at these given conditions. x0 is already here, and x1 is given. What is x1? x1 is w0. w0 is given to us. It looks like it is useless here for this calculation. And what about u2? u2 is also given to us, and it is x2 plus, sorry, and it is x0 plus x2. x0 plus x2. And x2 is, we know that, equal to w1. So we see that here, these random variables, x0 and w1, x0 is already given to us, and this is useless. I don't really care about this. But u2 is also given to us. So x0 plus w1 is also given to us. x0 is given, and x0 plus w1 is also given. So what does this mean? If I know both of these variables, if I know both x0 and u2, then I can calculate w1 deterministically from these two variables. How can I calculate it? W1 becomes just u2 minus x0 in terms of these given conditions. So then what happened? I know x0 deterministically in the given condition, and I know w1 deterministically. I can calculate it deterministically using the given conditions. So let me substitute this w1 information there. That is equal to probability of 2 u2 minus x0 plus x0 smaller than or equal to psi 3, x0, x1, and u2 here. And I can calculate this as 2u2 minus 2x0 here plus 1x0. So I have minus x0 being smaller than or equal to psi 3, x0, x1, and u2. Now you see that I know all of these quantities on the left here deterministically due to the given conditions. Okay? That means that this event, this 2u2 minus x0 being smaller than or equal to psi 3 is just a deterministic event. It's no longer random. It either happens or it doesn't based on the given conditions. So its probability is either 0 or 1 depending on the given values of x0 and u2 here. Okay? Well, let us write this. This is equal to, the probability is 1 if this condition is satisfied, 2u2 minus x0 smaller than or equal to psi 3, and it is 0 if this condition is not satisfied, 2u2 minus x0 greater than psi 3. Okay, I don't really have to put this. Now I would still need a better functional form for this type of distribution. That is a CDF actually. I can write this as 1 if psi 3 greater than or equal to this deterministic number 2u2 minus x0, and this is 0 if psi 3 is smaller than 2u2 minus x0. So in order to be able to express this CDF, I will define the unit step function here. The unit step function, u of x, I will show it with capital U of x. We know that it is 1. I'm defining it to be like this. And it is 0 if x is smaller than 0. That is my unit step function. And what happens if I shift this function? U of x minus x bar. This is a shifted step function. Or the step function looks like this. The original one. This is x and this is u of x. What happens when I shift this function? That function would be given to me as 1 if x is larger than or equal to x bar, and this x bar is a deterministic number, and I have 0 if x is smaller than x bar. Okay? So you see that here, this function that I give is nothing but a shifted step function. Okay, shifted unit step function, and that is given as u of, I would have the argument of the function as psi 3, and it is shifted to this deterministic number. Okay, 2u2 minus x0. This is my CDF here. I can now erase these. So now I can write my result here. This is u of psi 3 minus 2u2 minus x0. Okay? In order to be able to calculate this PDF, I need to take the derivative of CDF with respect to its argument, and that is going to give me this PDF. Okay? Let me write this PDF then. x3, x01, u02 here. Just the derivative of this thing with respect to psi 3, then I would substitute x3 instead of psi 3. Okay? The derivative of the unit step function is going to be an impulse function. And the argument will remain the same here because derivative with respect to psi 3 of the argument is going to give me 1. And I would have here x3 minus 2u2 minus x0. So this is the first PDF that I need to calculate. All right? It is an impulse function. Now let us try to concentrate on the second PDF. In order to be able to calculate this PDF, I'm also going to be looking at the corresponding CDF. Fx3 given x1 and u2 here, okay? And I will have psi 3 again. So this is probability x3 smaller than or equal to psi 3 given x1 and u2. And I know what x3 was. It was 2w1 plus, what was it? Plus x0, okay? Smaller than or equal to psi 3 given x1 and u2. So here, let us concentrate on the given conditions. x1 is w0 and u2 is here, is nothing but x0 plus x2, which is x0 plus w1. So I know here deterministically what x0 plus w1 is, but I really don't know the individual values. I know only the sum of x0 and w1. I don't know their individual values, so they would still remain random under these conditions. But here you see that this is nothing but w1 plus x0. I know what that w plus 1 x0 is. Okay, so this event is equal to, I have w1 plus x0 plus w1, which is given here as u2, smaller than or equal to psi 3, x1, and u2 here. Okay? So now this u2 here is deterministic. Let me take it to the other side. P w1 smaller than or equal to psi 3 minus u2 given x1 and u2. So you see that I get an event in terms of the random quantity w1 here. Okay? Do you think I can remove here the given conditions? x1 is w0. W0 really has nothing, has no information about this event. I can remove here x1. What about u2? u2 is x0 plus w1. So you see that u2 is dependent on w1. As a result, I cannot remove this u2 still from this condition. Okay? So u2 should still remain here. But I can remove what x1 from here because x1 is just w0. These are deterministic and w0 has no information about w1 whatsoever. So I can write here this as pw1 smaller than or equal to psi 3 minus u2 given u2 here. And here I can definitely not remove u2. Remember in the earlier lecture, in the previous lecture, we calculated such a PDF. So we are going to convert this into a PDF, and if the variables are Gaussian, I can calculate the expected value of W1 given X0 plus W1, okay? Or I can calculate the covariance. If the random variables were jointly Gaussian, if they were given to be individually Gaussian, then I could have calculated such a probability distribution or such a PDF. So this is nothing but another CDF function. So let me write this. F of x3 given x1, and I have u12 here. This psi 3 is equal to this is, I can write this as the CDF of the random variable w1 given u2 evaluated at psi 3 minus u2. Okay? Then let me convert this into a PDF. And that is going to be P of x3 given x1, u12, and that is equal to, take the derivative of this function with respect to psi 3, it is going to be the PDF of W1 given u2 evaluated at psi 3 minus u2, but instead I need to substitute x3 instead of psi 3. x3 minus u2. And this was the first PDF that I needed to calculate, and this is the second PDF that I needed to calculate. Remember, if the PDFs of the individual random variables W1 and x0, which determines the distribution of U2, if they were given to be Gaussian, then I could have calculated such a Gaussian by calculating the mean of W1, which given x0 plus W1, and mean covariance of W1 given x0 plus W1 using the conditional Gaussian formulas. And then this density would be a non-degenerate Gaussian distribution, and in it I need to substitute x3 minus u2, and therefore it would never be equal to this impulsive distribution here. It would have a non-zero covariance in general. As a result, these two distributions really are not the same. And what was the reason for this? Here we are actually going to see that the reason that these distributions do not turn out to be the same is this feedback rule. Okay? This feedback rule changes everything here. Okay? And what is bad about this feedback rule, which have caused us to lose Markovian type of property there in those PDFs, is that this feedback rule is dependent on the previous states or previous measurements it can depend on. Okay? So here, the reason that we don't have equality here is that this feedback rule in U2, it depended on the input depended on the previous state. Okay? What is the problem? What is the problem that made this type of feedback problematic in terms of Markovianness? So let me look at the given conditions here. In the first distribution, I have x0, x1, u0, u1, u2. We know that u0, u1 doesn't bring us any information whatsoever. So the given conditions in the first distribution were x0, x1, and u2. Okay? And what about the second distribution? If I do the same thing to the second distribution, the given conditions for the second distributions were, so I had x1 and u2. Okay? Here, remember what u2 was. u2 is x0 plus w1. So this u2 is x0 plus w1. And here we are trying to calculate an event related to x3. And x3 was just this. Where is it? 2w1 plus x0. 2w1 plus x0. Okay? Is this really correct? X3, yes, that is correct. And I can actually write this as u2 is given, And I can actually write this thing as follows. So I have U2 is given in both of them. So I have x0 plus W1. I know what x0 plus W1 is. That is, x3 is nothing but W1 plus U2. Okay? U2 is x0 plus W1. X0 plus W1. As a result, I know actually what x0 plus W1 is. If I substitute U2 here, there is an excess of W1 here. Okay? So here, I'm trying to calculate a probability related to x3, and probability related to x3 would be related to a probability with respect to W1. The distribution would be related to W1. Okay? Here U2 are given in both conditions, x1 are given in both conditions. There is only this x0 which is extra here. And if I could remove this x0 from the first conditioning, then both distributions would be the same. But here you see that the addition of this x0 into the first conditioning here changes the distribution to an impulse. Why is that? Because the feedback input U2 was x0 plus W1. If I know U2 and if I know x0, I know exactly what W1 would be. Therefore, x3 becomes deterministic as soon as I include here the knowledge of x0 here into the conditioning. On the other hand, in the second conditioning, x0 is not given. As a result, W1 still remains as a random variable. Okay? With a non-degenerate distribution, non-impulsive distribution. So you see that this is caused due to the dependence of U2 on x0. If I remove this x0 from this feedback, then things would be the same. Why is that? Because you see that in that case this U2 would be just W1. Would it be the same? No, maybe it's not the same. But here the dependence of the input on the previous outputs or the previous states here caused a drastic difference in these PDFs here. Okay? So here, what do we have to do in order to get rid of this type of dependence? Okay. So one idea is to make the state only a function of the current state. Okay. One idea is to make the input a function of only the current state. But does it really work here? So you see that in the original case, I had 2W1 plus x0 as my x3. So you see here that, but did it depend on that one? Sorry, I will just try to write what happens when we have no dependence of the input on x0 here. Let us say that instead of this U2, I have just x2. Okay? Let us say U2 is just x2. In that case, what would happen to the given conditions? What about x3, for example? x3 is equal to x2 plus U2 is x2, and x2 is W1, so I have 2W1 here. All right? So now let me write these given conditions. X3 is 2W1 in the case that the input doesn't depend on the previous outputs. In that case, I will write the given conditions X0, X1, and U2. And U2 is just X2, so I would have, and in the second one, I have X1 and U2, okay? So in this case, U2 is just X2, but X2 is W1, okay? So W1 is given to us, and I'm trying to calculate the density of 2W1. So you see that in that case, these X0 and X1 would not really change anything. So I can actually remove this X0 from here. It would not give us any information whatsoever about this 2W1. So you see that one solution of getting rid of these distinction between these distributions is to make the input only a function of the current state. So instead of using or the current output, so instead of using the feedback rule, UK equals to GK Y0K, I don't want this past dependence on the outputs. I can instead only write GK of YK, okay? This would really fix things, as you see here, because we are trying to calculate the probabilities of 2W1 given these or these. But as soon as U2 is given to us, which is W1, really the other information is not important. So I can remove X0 from here. Then I would have two impulsive distributions which are the same. So these two distributions in that case would be the same. So one solution, therefore, to recover Markovian property for a feedback system, a stochastic system, it is to make the input depend on only the current output. That is one solution. And we are actually going to be able to have such a solution in the future parts of this course. In the book, in this chapter that we are covering, another solution for the same problem is actually adopted. And the solution that is adopted for recovering Markovian property for this example is to choose U2 not in a feedback rule, but choose U2 only as a deterministic variable, okay? Choose U2 like this. So just remove this feedback rule from here and choose U2 deterministically. In that case, you can actually show that these two, of course, everything would change for these distributions, but you can actually show that the Markovian property is also recovered if you choose only U2 deterministically, and if you leave this U0, U1 as they are. So what did we say so far? So far we have seen that if we assume basic random variables to be independent, then one-step transition PDFs would always have a Markov property. But we could still have a problem in the case of multiple step transition PDFs, more than one step transition PDFs. They might not have Markov property if we have a feedback rule that would depend on past outputs or past states. Okay, and this example was illustrating that. And so far I have told you two solutions for that. The first solution is to assume that this problematic input to be deterministic. That is what is adopted in the book. Okay? And a second solution, which is going to be seen in the future parts of this course, is to select this input again using in a feedback form, but do not allow this input to depend on the past states or past outputs. That would solve the problem as well. But here, in this chapter in the book, only the first solution is selected. So, and what is that solution? That solution is to select this input, this problematic input U2, deterministically. So not using a feedback, but choose it deterministically. Okay? And that is actually what we are going to, that solution is going to be what we're going to cover in the next lecture. So this lecture, therefore, is complete. That's all for this one. Bye.